Okay, so this is our 5th lecture on linear programming, I think the 3rd lecture on linear programming itself. And so today we're actually going to be proving some of the key theorems to analyze these problems. And so we're going to start with a quick review of canonical form. And so we were talking a little bit before class started about why you would want to put something in canonical form. And the reason is it sets up the system of equations, it sets up the problem so that you can use algebra in the same way. So you know exactly what form things are going to be in. So the canonical form is going to look like ax equals b, the vector x is greater than or equal to 0, and you want to minimize, say, x transpose c. And to be really specific, a is m by n, so this is the number of rows, this is the number of columns. X is going to live in, so if x is hitting a like this, x has to live in Rn, c has to live in Rn, and then b lives in Rn. So we talked how any linear programming problem can be put into this form. We talked about how we can assume x is greater than or equal to 0 by, if necessary, writing something xi as yi minus zi. And doing a nice little trick like that, we can assume all of our variables are non-negative. If we ever had instead of equals, if we had a less than or equal to, we talked about how we could get rid of the less than or equal to by just adding a new variable. And if there was a greater than or equal to, we could get rid of that by multiplying. So first we were able to assume everything was less than or equal to, then we dropped the less than. So a canonical problem is going to be of this form. And so our goal is to find optimal solutions. And so for us, an optimal solution is going to minimize this linear function x transpose c. So this is just minimize c1 x1 plus cn xn. And again, if instead of trying to minimize a function, if you wanted to maximize a function, the only thing you would have to change is replace c with negative c. So we can really do maximization problems as well, but just to have a common language, we can now say we're going to be minimizing. And if you want to think back a little bit to the geometry classes you had, when you had to draw something on paper. And this way we know which way we're drawing things. We kind of know, it's the analog of knowing what the angles are. It's going to be a minimization problem. That just gives me the language to use. Alright, so the first question is there a solution? So, if these two are satisfied, we say we have a feasible solution. So again, our goal is to find a solution to this that minimizes x transpose c. But before we can even try to minimize x transpose c, the first question to ask is there a solution? Is there an x that satisfies ax equals b and x is greater than or equal to 0? Well, if we think about it, A has n rows and n columns, X has n entries, B has m entries. The only chance for this to really be interesting is if we have an undetermined system. If, m equals n, then basically there's either one solution, essentially, for most part, right? So the problem is, if it's an overdetermined system, then there's basically no chance of it working. And if I give you 2x plus y equals 3, 3x plus 2y equals 7, 4x minus 21y equals 8, I've given you more equations than unknowns. We don't expect there to be a solution in a situation like that. So if I have more equations than unknowns, I don't expect anything interesting. So the only chance to have something interesting is if we have an undetermined system. And then there may or may not be a solution. So we want undetermined systems. Undetermined systems. So more variables than equations. And so thinking about what m and n is the number of variables we have, m is the number of equations, so we'll want basically m to be greater than n. Okay. So we've talked about what it means to be a feasible solution. An optimal solution is a feasible solution that minimizes this. Okay? So our search for optimals, we first look to see, is there a feasible solution? If there's no feasible solution, could there be an optimal solution? No, right? So then, once we have a feasible solution, we look at all possible feasible solutions and see which one of them minimizes this. So the first question to ask is, if I give you a generic linear programming problem, does it always have a feasible solution? If it has a feasible solution, does it always have an optimal solution? So the first question is existence. Okay. So, again, the very first question you can ask about any mathematical object is, does it exist? So question 1. Do we always have a feasible, optimal solution? This is the existence question. So let's assume we have a linear programming problem, and let's assume we have a feasible solution, and let's assume we have an optimal solution. What's the next question you would ask? So we know it exists. So there's a list of math questions. The next question, once you know it exists, what's the next thing you ask?
What is it?
So what it is, can we find it? Can we find it? It might be the wrong word there. There's another math question we've missed.
Uniqueness.
Uniqueness, right? Once you know something exists, then you want to figure out, is it unique or are there others as well? So question 1 is obviously the simplest. Then I think question 2 and question 3 are going to compete with each other. Okay, so let's first go through and show that sadly it's not always the case that we have a feasible solution. It's not always the case we have an optimal. And then even if we have these, it's not always the case that it's unique. Well, sometimes it might not matter if it's unique or not. If we have an optimal solution, does it matter if there's another optimal solution? If you're trying to maximize your profit, if I tell you this allocation of resources will maximize your profit, do you care if there's another allocation that gives you the same profit?
Sometimes.
So, okay, so why would you care?
For example, if you prefer certain food and there are 2 solutions and one solution.
So then the question is, are there other factors that are not incorporated in our problem?
Yeah.
Right? So for instance, when we were doing the diet problem, maybe we prefer ice cream to M&Ms or steak to Cheerios. And so if there is something like that, then we might actually care about which of the different optimal solutions we are. Other questions could go with the stability of the model. We have to estimate these values for these equations. It might be that some of these guesses are a little bit off. And then the question is, if we're a little bit off, how bad is the effect going to be? And so it could be the case that one optimal solution is a little bit more robust, is a little bit more stable. If you think back to the simple harmonic pendulum, unfortunately I have a limited budget. If you have the pendulum swinging like this, there's 2 equilibrium points. One is straight down, and if I displace it just a little bit, it'll move a little bit, but it won't change that much. And where's the other equilibrium?
Straight up.
Straight up, right? This is not a stable equilibrium. A slight push here will get it really swinging far. And so it could be the case that even though there are different solutions that have the same revenue, that have the same value, maybe one in some sense is more stable than another. So it could be useful to go for methods that will generate all of the feasible solutions, all of the optimal solutions, and not just a subset. These are more advanced issues. The first thing is, can you find an optimal solution? Once you get that, then you can worry about which optimal solution do you prefer. So let's example 1. And these are the same examples as in the notes. So let's take x1 equals negative 2007, so you can tell when this example was made. And we'll take x1 to be greater than or equal to 0, and then we want to minimize 10x1. So are there any feasible solutions to this problem? There's no feasible solutions. x1 has to be non-negative, and we want x1 to be negative 2007. So here, I'm taking a very simple choice of A. A is a 1 by 1 matrix. In fact, it's the 1 by 1 identity matrix. Okay. No feasible solution. So if you're looking at this, your first thought should be, come on, this is, too stupid of an example to really be worth our time, right? I disagree. I think examples like this are terrific, right? Always look at extreme cases. This simple example is enough to tell us that it is not the case that every canonical linear programming problem has a solution. So we're going to have to be careful. Now, fortunately, a lot of the things that we're going to study later in the semester have to have a solution from either physical or economic grounds. If you run a movie theater, you're going to have to come up with a schedule. Which movies to play on which screens at which time, and you want to maximize your profit. Can you come up with a schedule to play the movies on your screens so that there are no conflicts? You don't have two movies playing on the same screen at the same time, all these natural constraints. Can you give me a schedule? You have 13 movie screens, you have 18 different movies, you have slots of every 5 minutes. Can you give me a schedule of movies where there will be no conflicts? There's a very simple solution. What's the solution? So I don't want to ever use the same movie on two different screens at the same time. I don't want to have two movies on the same screen at the same time. I don't want to take a movie off the screen until it finishes running. Can you give me a procedure that will guarantee that this can be satisfied? Think very simply.
Every screen just for one movie?
Be simpler than that. That's too complicated. Don't put movies on, right? Be even simpler than that, right? Give me the simplest possible schedule that will satisfy all constraints. What's the simplest thing you can do? Show no movies, right? If you show no movies, are there any conflicts? So there's a feasible solution to the movie problem, right? Don't show any movies. There's a feasible solution to the airline problem. Don't fly any planes. You're not going to make any money. Okay? But this shows you at least that there's a feasible solution. So for a lot of the problems we're going to look at, it turns out that there will always be a feasible solution. Example 2. So now we're going to look at 2x1 minus 5x2. I forgot to write down what I want this to be. Oh well, alright, so let's make this equal 10. We want x1 and x2 to be greater than or equal to 0, and we want to minimize negative 17x1. So is there a feasible solution to this? Yeah. So feasible, take x1 equals 5, x2 equals 0. And in fact, there's going to be infinitely many feasible solutions. I can keep increasing x1, and then I just start increasing x2 to compensate. And basically, every time I increase x1 by 5, I increase x2 by 2. So I'll have infinitely many. Is there an optimal solution? Is there a solution that minimizes negative 17x1?
Yeah.
No.
Right. That seems to...
Okay, so if I take x1 equals 0,
Yeah.
I get my minimum is 0.
Yeah.
Can I get something lower than 0?
The thing is that you can keep increasing.
I can keep increasing x1.
Yes, you can do that forever.
I can make this cost as small as I want, as negative as I want. Because x1 and x2 are both positive. So if I take, so there's no optimal. can take x1 to be, I think, 5 plus 2m, and x2 to be 5m. And if I do that, they'll both be positive if m is positive. And when I plug them in here, what's going to happen is I will get 10. Because so I mixed up this time. Sorry. This should be a 5 over here, and this should be a 2 over here. Now I'll get 10. So I'm actually able to parameterize my feasible solutions in this case. I can write them down in an explicit, nice form. And when I do this, I see that I can always satisfy this constraint. My x's are non-negative, and I can make my cost as negative as I want. So there's no optimal solution. So just because a feasible solution exists, just because infinitely many feasible solutions exist, sadly does not mean that there must exist an optimal solution. Okay, so the last one to consider is the following. x1 plus x2 equals 1, x1, x2 greater than or equal to 0, and we want to minimize x1 plus x2. And again, this is a special cooked up example. Now notice, just like everything else, we have more variables than constraints, than equations. So this is an underdetermined system, so we expect there to be many solutions. Are there feasible solutions to this? Yeah. In fact, all the feasible solutions, they're the form t 1 minus t for t in 0, 1. And so again, I can write down an explicit formula for all the feasible solutions. This is rare, but when you cook up your examples this much, it's not surprising you can do something like this. Okay, which feasible solutions are optimal solutions? Every, right? Every feasible is optimal. Right? This is not the typical situation in the world, right? If you just randomly choose a schedule of movies that doesn't conflict, or you randomly choose flights for planes, that's not going to give you optimal revenue. But it's possible to have a situation like that where every feasible solution is an optimal solution. Alright, so this gives us an example of what can go wrong when we're looking at linear programming problems. Now, a lot of times in the real world, there shouldn't be situations like this. We should have basically one optimal solution, or something close to that. Okay. So the next thing I want to talk about is the chess problem. So 1, 2, 3, 4, 1, 2, 3, 4. So the situation was we had a 5x5 board, we had 5 queens, 1, 2, 3, 4, 5, and we had 3 pawns. And the goal was to place the queens on the board in such a way that the 3 pawns could be safely placed down. And again, just in case the point hasn't been made enough times, I do not care about placing pawns on a 5x5 chessboard to be safe from attacks by queens. But why is this problem important? Well, there's a lot of things in life that you can solve by brute force. If I ask you to tell me if a number is prime, what you can do is you can keep dividing every number smaller than it until you reach that number. If the number I give you is even modestly sized, you'll go crazy. Or you'll run out of computer time. You start to find better algorithms to tell if a number is prime. And so here, we can look at all the different ways to place the queens on the board. How many ways are there to place 5 queens on a board?
25, choose 5.
Good. So there's 25 choose 5 ways to put 5 queens on the board. So this is 25, 24, 23, 22, 21 over 5 times 4 times 3 times 2 times 5. Alright, so if you go through it, you'll see that there's a large number of combinations to try. You can try to write a computer program to do this. And there's various ways you can do this. one way you could do it is you could actually label the squares 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you need to just choose 5 numbers. And your first number can be anywhere from 1 to, I think, 21. Because your first number will be the location of the queen that's at the lowest square. And if you do the coding like that, it's not so bad. So maybe 1 plus equal to Q1 plus equal to, I think, 21. Q1 less than Q2 plus equal to 22. Q2 plus equal to Q3 plus equal to 23. Something like that. So this is one way to go about the problem. There's a better way to go about this. And so here, notice we're looping on 5 things. We have 5 things we have to play with. Rather than putting down 5 queens and try to see which squares they don't attack, what if we put down 3 pawns and then look at all the squares that can attack them and see what's left over? Change our perspective and look at it from the pawn's point of view. How many ways are there to place 3 pawns? So if I want to place 3 pawns, 25 choose 3. So this is 25, 24, 23, over 3 times 2 times 1. So the difference is 22 times 21 over 5 times 4. 5 times 4 is roughly 21. So this is 22 times faster. Now, computers are so fast that the computer can do either of these by brute force. It's not really much of a savings here. But the principle is very important. Depending on how you look at things, you can make huge differences in terms of runtime. And with linear programming, runtime is going to be the critical issue. Typically, you cannot afford to wait till the universe expires trillions of times over to get your results. You want something in a reasonable amount of time. And so savings like this are very important. And it's absolutely amazing. I mean, it's the same problem, but looking at it from the point of view of the pawn versus the point of view of the queen, you can do even better. Rather than doing the chess problem, I'll just do tic-tac-toe. One of the greatest games ever invented. How many opening moves are there in tic-tac-toe for a mathematician?
What is that?
So, you've never played tic-tac-toe? So tic-tac-toe, you put down X's and O's, and whoever gets 3 in a row wins.
Oh.
And you get either 3 in a row horizontally, vertically, or diagonally. So, where would you like to go? You get to choose.
The middle.
Middle. I'll be stupid, I'll go here. Your turn.
So
You have 3 seconds. Where do you want to go? You have 3 seconds. Which one? Here?
yeah, sure.
Alright, I'll go here. You have 3 seconds. Where do you want to go?
The one above the center.
The one right here. And now I'm dead. Because you're attacking me 2 different ways and I can't defend both. So, once you went into this, it was actually a mistake for me to go here. There's not that many possible tic-tac-toe games to analyze. Right? There's only 9 squares. There's 9 factorial ways to put things down. Now, 9 factorial is not small, but it's doable. But from a mathematical point of view, I'm a mathematician. How many opening moves are there for a mathematician in tic-tac-toe? It's not 9, it's smaller than 9. What are the possible first moves?
Like the middle and then yeah, 1 and then the one next to 1, 2 on the right.
And what else is the same as 2?
And then the 4 same.
Okay, so these are all 2.
These are all 2s, and then the 4 corners.
So there's really only 3 open moves in tic-tac-toe. By symmetry, if you go here, if I just flip the board, that's the same as going here. If I rotate it 90 degrees, that's the same as going there. So really, there's only 3 opening moves, and you can use the symmetry to really prune down the analysis. This is how, back in Williamstown, I was undefeated on the elementary school playground in tic-tac-toe. None of the kids could beat me. Worst I ever did was I tied one game. How many opening moves are there for placing the first pawn? So now on the 5x5 board,
The first one is center.
good, where's 2?
The right is the one right there.
So that would be 2,
And 2, yeah. 3.
and then 4 here. And then this 4 is the same as that. So then coming down here, 4, 4,
Yeah.
4, 4, 4, 4,
Yeah.
5,
5.
and then 6. So if we do that, it's even better. There's only 6 opening moves for the pawn. So again, using these symmetry arguments, you can often really trim the possibilities. Okay. Alright. So what does the chess problem have to do with linear programming? The idea here was look at what we'll call the dual problem. So basically, if I give you a problem, sometimes there's a related problem, and it's easier to look at that related problem than the original problem. Sometimes just changing your vantage point helps. You might have seen this in telescoping sums. If I give you 2 minus 0 plus 4 minus 2 plus 17 minus 4 plus 661 minus 17 plus 2012 minus 661, what does that equal?
2012.
Should just be 2012. The 2's cancel, the 4's cancel, the 17's, the 661's cancel. And so if I look at the problem horizontally, that's going to be a lot more time consuming than looking at a diagonal. Changing this perspective is powerful. And so looking at a dual problem is basically changing your perspective and looking at a related problem. I'll give one other example where you may have seen this. In high school or junior high school, you might have done conic sections where you have some kind of cone, and for some reason you're mad at it and you slice it with a plane, and you look at the different shapes that come out. And one of the shapes you can get is an ellipse. And so you can write down the equation for an ellipse like this. We've got x over a squared plus y over b squared equals y. And so this is the equation for an ellipse whose axes are parallel to the coordinate axes. What if instead I give you an ellipse like this? Now you're going to have cross terms, you're going to have xy terms, x terms, and y terms. It's a mess. What should I do?
Shift the axis.
Shift the axes, exactly. I should use these new coordinate systems, u and v. In uv space, you look like this. My ellipse is now aligned with the coordinate axes. And I have a nice equation for the ellipse in this uv coordinate space. And then I use linear algebra to rotate back to the xy basis. So this is where you would use rotation matrices. So the idea is, this is something you've seen many times before, is that it's a good idea to take a hard problem and try to find a way of re-expressing it to illuminate different features. And that's what the dual problem is going to do. So I've been deliberately leaving the canonical form over here. I'm now going to write down the dual problem. And so if I give you a canonical linear programming problem like this, the dual problem is now going to be solved y transpose A equals C. I think there might be a greater than equal to, let me check. Yeah, so less than equal to. And here, y is actually a real vector. And I always have to think for a moment as to what's the dimensions of everything. So A has m rows and n columns. Y I'm now going to be writing it as a row vector. So I have to have the same number of columns in y transpose. as rows of A. And so I believe Y has to have M elements. So Y should be an Rn. And then this will tell us over here, C is going to be an Rn. Well, good, because that's what C had to be from before. And so the dual problem is a little bit different than the canonical problem. Here we actually have an inequality. And here we're allowing Y to have non-negative elements as well as negative elements. And so the question is, why is it worth considering the dual problem? So the first thing is, does it seem like the dual problem is related to the canonical problem? Can you see any relations, any commonalities? A. So they have A, which is good. What else do they have? There's one other thing they have in common. They also both have C. So if I look at the dual problem, I have the same matrix as before. The difference now is, instead of having B and having X on the right, I have Y on the left, and I have C coming over here. You'll notice that something is missing in the dual problem. Right? What's missing? What's that? We're missing something from the canonical linear programming problem. It did not make it over here. What's missing?
Oh, there's no objective.
So good, there's no objective function. No objective function. What else is missing?
The constraint for Y.
Well, we have a constraint. It's a different constraint, but we do have a constraint for Y. But there is something else that's missing. Something else that's on this side that didn't make it over.
X greater than 0.
So X is missing. So X is basically replaced by Y. But there's something else.
Inequality? It's not. No.
What? There's something on this side that's not on that side. What's missing? So there's a symbol here that doesn't make it over.
Also equal sign.
There's an equal sign. B.
Oh, B.
Right? There's no B on this side. Right? So this side has both a C and a B. C is coming in the minimization function. B is what I want my constraints to equal. On this side, I have my C transpose. Okay, that's the same as C. It's just a transpose. Going from row to column or column to row vector. That's not a big deal. I don't have X, but instead of the variable X, I have the variable Y. So Y and X are kind of replacing each other. I lose the equalities and I get inequalities, right? But the real thing is that I don't have B anymore. Okay? So these are related. They're not the same, but they're related. Okay, so now, the problem is we have very limited Blackboard room. I'll try to do it down here so we can keep everything. And I'll fill the missing with any space. So we have the following lemma. Say Y is feasible for the dual, and X is feasible for the original problem. Then Y transpose make sure I write down the right way. Yeah, it was Y transpose. Okay, then Y transpose B is less than or equal to X transpose C. So the first thing to check is always, is what I've written down reasonable? Well, X and C have the same dimension. So, X transpose C is the same as X dot C. That makes sense. They both live in Rn. Y lives in Rm, B lives in Rm, so yes, this makes sense as well. So let's see why this is true. So proof. We know Y transpose A is less than or equal to C transpose. So what I'm going to do is I'm going to rewrite this in a more illuminating way. Rather than writing it as X transpose C, what's an equivalent way of writing this? X transpose C is the same as... basic. C transpose X. So why would this be useful? Well, we know Y transpose A is less than or equal to C transpose. Let's multiply the right of each of these by X transpose. So you get Y transpose AX is less than or equal to C transpose X. But what do we know about AX? Well, since X is feasible for the original problem, AX is just B. So we get Y transpose B is less than or equal to C transpose X. And that's what we wanted to show. This might be the first result we've actually proved in linear programming. Let's see why this is a great result. So does anybody have any sense as to why this is worthy of celebration? Why should we be happy that we've proven Y transpose B is less than or equal to C transpose X? How can this help us?
Have some way to relate B to C.
So we have some way of relating B to C. Well, B and C are both given to us. So, whenever we're doing this problem, somebody tells you what B is, someone tells you what C is. They give you the objective function, they give you the constraints. Mm-hmm. You're trying to find an optimal solution.
Oh no, I mean like this, maybe the relationship between X and Y is more important. I don't know, because they are two different problems and now suddenly you have two visible solutions related to each other.
Good, so we have some information going forward. So this tells us that information on one problem gives us information on the other problem.
Yeah.
And so in particular, let's say you're trying to maximize profit for American Airlines. I know we're supposed to be doing minimization, but when I talk about an actual company, I just cannot say minimize profit. It just bothers me. Okay? Let's say you're trying to maximize profit. It would be nice to know what your theoretical best is. It would be nice to know ballpark, what can you expect to get. What this is telling us is, well, if we have an optimal solution, any optimal solution has to be feasible. This tells us every feasible solution, this is going to be what your revenue would be. It cannot be lower than Y transpose B, where Y is a feasible solution of the dual problem. So as soon as we get one feasible solution to the dual problem, we have a lower bound for the minimization problem. That's extremely useful. That gives us some idea of how close we are. So for instance, let's imagine that, maybe we're trying to minimize unhappiness. We'll use some absurd scale. And, this tells us that, the the unhappiness in the world with our current economic and political policies has to be at least 1,005. And we have something that will give us 1,005.2. We're probably then pretty close to minimizing unhappiness subject to our constraints. It tells us when we're very close. If instead we have that this is 1,005 and this is 2.7 trillion, maybe we can do a better job. And so this leads to a very natural theorem. So, theorem. assume y hat, x hat are feasible solutions to the dual and original problem, and y hat transpose b equals c transpose x hat. So they're actually equal. Then x hat is optimal. So this gives us a way, theoretically, to find an optimal solution. If we can somehow find two feasible solutions such that this relationship holds, then we're in great shape. And so the question is, why is this true? Well, if we look at this, we know y x feasible implies y transpose b is less than or equal to c transpose x. So if I look at the optimal here has to be greater than or equal to any feasible thing here. And so if I have that this equals for this special one, is it possible I could have a lower cost? Well, imagine I had a lower cost than this x hat. If I had a lower cost, then there would be, if I just take that special value of y hat in here, so if, I'll do some kind of script x gives a lower cost, then y hat transpose b would be greater than c transpose strange x, which is a contradiction. So it's worth thinking about this for a moment. This is the key idea. If I have an equality here, if I could somehow lower the cost, then I would no longer have this is less than this for all choices of feasible y's. There'd be at least one choice of feasible y, this special y hat, where this fails. So there can't be any x's that have a lower cost than this. So there is no lower cost than this. Alright, so the full details of this, if this isn't quite there, are in the notes. But this is a monumental result. We've reduced all of linear programming to just happen around somehow to find a feasible y to the dual problem such that this is true. Of course, the question is, how easy is it to find a situation like this? How easy is it to solve the dual problem? Once we solve the dual problem, how easy is it to find the feasible y such that this equality holds, as well as finding the feasible x such that this equality holds? So right now this is a theoretical triumph and a practical nightmare. Right? There's no good constructive way of getting to these values yet. This just says, if you happen to find them, great, but good luck finding them. Okay, so from an implementation point of view, we're still not happy. But at least from a theoretical point of view, we are making progress. And we have some idea of how to attack, and we also have some idea of how to tell how close we are. So if you do go back to the situation where you own American Airlines or you own a movie theater, you could compare your revenue or your schedule, whatever, with the prediction, with the balance you would get from solving the feasible problem. And you can get some sense of how close you are. So again, you won't know if you're at the optimal, but you might get some sense as to how far away you are from optimal. And if you're measuring profits in the billions and you're off by $1 million, it's not necessarily huge. Okay, any questions on what we've done so far? Okay, so the next thing is, now that we have the concept of a feasible solution, we're going to expand it and introduce some new notation. And so I said that today's lecture is the basics lecture, and so we're going to get to basic, feasible, and basic optimal solutions. Basic, feasible solution. So let X be a feasible solution of our canonical linear programming problem. So X equals x1, x2, and I always forget, did we say X has m coordinates? X has m coordinates. And let's say xl1, xl2, xlk are the non-zero elements of X. And remember, in the canonical linear programming problem, we assume that all of our coordinates are non-negative. So you have two choices. You're either 0 or you're positive. And so this is where we can begin to see the usefulness of canonical. Right? Because we have something in canonical form, these entries are either positive or 0. I don't have to worry about negative. And it's going to be very useful later on. So now, this is an advantage of canonical form. Okay, so let AI be the ith column of the matrix A. Okay? So AX is the same as A1 x1 plus an xn, or if you want x1 a1 plus xn an. So we talked a little bit about this in the linear algebra review at the start of the semester. If I'm looking at this matrix multiplication, what do I have? I have my matrix A, I have x1 through xn, I have my column a11, a21, am1. And when I multiply it out, it's the same as multiplying the first column of A by x1, the second column of A by x2, etc., 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 and then add. So when I look at AX, it's really this. But of course, all that really matters are the non-zero elements. Right? Because any x that's 0, the corresponding column doesn't matter. So this is the same as x L1, AL1, plus xlk, alk. So we say X is basic if the columns AL1, AL2, ALK are linearly independent. So the definition of a basic feasible solution is, well, not surprisingly, to be a basic feasible solution, you first have to be a feasible solution. So if I haven't said X is feasible, X is feasible. And it's feasible with one additional property, that because X has only positive and 0 entries, you don't really care about the 0 entries because they don't come into play. Look at the columns that correspond to X being non-negative, to X being positive. Okay? And so if the corresponding columns are linearly independent, we then say that our vector X is a basic feasible solution. And so what does it mean to be linearly independent? It means that the only way a combination of these columns can be 0 is if the coefficients are 0. So V1, Vk are linearly independent if C1, V1 plus Ck, Vk equals 0, if and only if C1 equals C2, equals ck equals 0. That's what it means to be linearly independent. The only way a combination can be 0 is if everything is 0. Think of it as moving in the north, south, and east-west direction. The only way you can basically be at the origin if you move some amount north-south and some amount east-west is if you move 0 in each direction. If I give you, 3 directions in the plane, so this, then it's actually possible to have a combination that gets me back to the origin by going some amount in each one. Now I could go something like this, plus this, plus this. But if all I have is north, south, east, west, I can't do that. So this is the definition of a basic feasible solution. In the interest of time, I'm not going to write basic optimal. I'm going to ask you to tell me what's the change I make to get from basic feasible to basic optimal. I changed one word up here.
Feasible to optimal.
Yeah, basically, exactly right. Feasible becomes optimal. So when you're teching, or when I was teching, it was really easy. It was just a copy, paste, and change one word. Right? A basic optimal is basically an optimal solution such that the corresponding columns are linearly independent. Okay, so the question is, why do we care about basic feasible solutions? Why do we care about basic optimal solutions? It turns out, and we'll see this next time, that there are only finitely many basic optimal solutions. I'm sorry, basic feasible solutions. That's useful. Any optimal solution has to be feasible. And we're going to show the following. If there's a feasible solution, there's a basic feasible solution. If there's an optimal solution, there's a basic optimal solution. And a basic optimal solution will also have to be a basic feasible solution. There's only going to be finitely many basic feasible solutions. This is going to limit our search space to a finite number. It will be a large finite number. Too large of a finite number to be useful yet. But it's the first big step in solving the problem. It's going to reduce the problem to a finite number from an infinity. And that is real progress. And then the question is it sufficient to find a basic optimal solution? Well, if all we care about is the linear programming problem that's written on the board, if all we care about is satisfying the constraints and minimizing the objective function, then do you really care which of many optimal solutions you take? You just want one of them. If there are other constraints you have, if there are other concerns you have, put them in the model, right? And so to some extent, you could say, yes, maybe we have some preferences. But then our constraint function, maybe that doesn't change, but maybe our optimization function changes. I want to find the die that keeps me alive as cheaply as possible. Well, maybe not as cheaply as possible. Maybe I assign a weight of 99 to keeping me alive cheaply, and maybe a weight of 2 to my preference to ice cream. And maybe I start to somehow have more complicated objective functions to take into these different issues. So if you have these issues, you have to somehow incorporate them into the model. It can make the problem more difficult, and that's a challenge. So if you take the point of view that whatever you have is just the only problem you care about, everything I have is in the canonical linear problem that I've posed, then I don't care which of the many optimal solutions I find. I just want to find one optimal solution. And what this is telling us, or what we'll see next time, is that I can find, if there's an optimal solution, I can always find a basic optimal solution. And the basic optimal solution will come from a basic feasible solution. So it's sufficient to just look for solutions of this form. And that's going to be a great simplification. Okay, so we'll resume with this on next Wednesday.